Okay, so I realized as I was going through this earlier in the week that I split up the material a little bit strangely. It's not exactly the split between chapter 9 and chapter 10. I do a little bit of chapter 10 stuff in this lab, and there's a little bit of chapter 9 stuff that I don't do, but I think that this lab has just about everything you need to do the homework that I had initially set due for Friday, but I'll extend that deadline. So the lab starts with a bunch of packages. I think you don't actually need the Mosaic package or the LM test package for this lab, but I'm not 100% sure. I'll try commenting them out and maybe we'll have to bring them back. But we've got the tidyverse package, which I think we're all pretty familiar with at this point. We've got the skimmer package, which I show a lot. The Mosaic data package is just a data package that I'm getting my data set from. And then the package that's really new today is the Broom package. And we'll talk more about it when we do the second lab about logistic regression. But Broom is a way to tidy up statistical models. So we've talked a little bit about tidy data. We're using the tidyverse. And our model objects are not tidy. And so the Broom package is to like clean up, like you sweep with the broom your model to make it into a tidy data set. So for this example, I'm not going to use the football data. I'm going to use this data set that comes with Mosaic data. It's called Wickham, W-H-I-C-K-H-M. And I always have a hard time typing it because it's very similar to the last name of the guy who wrote the ggplot2 package and a bunch of the other tidyverse. His name is Hadley Wickham, and his last name does not have an H in it. Well, I guess it has an H at the end, but not at the beginning. And so I often misspell it. But this data set actually has nothing to do with him. It's from the electoral roll in Wickham, which is a mixed urban and rural district near Newcastle upon Tyne in the UK. This is, I don't know, from the 1970s. They did this study on a bunch of women to study heart disease and thyroid, and then they followed up on them 20 years later. So just, I guess, as a warning about logistic regression, it's often kind of morbid because alive and dead is a really good binary variable. There's kind of no in between. You're either alive or you are dead. And we can't, argue, well, I really like, sort of room temperature coffee. And so we need a third outcome variable there. Nope, you're either alive or dead. And then this has a categorical variable, which is whether the person smoked when they initially surveyed them, and then their age at the time of the first survey. So we're going to try and predict if someone is alive or dead based on whether they smoked and how old they were at the beginning of the survey. So I'm going to do some plots. So this is one that is similar to the one from the football data example that I was giving you. Here I've got dead and alive, and then I've colored the points by whether or not they're a smoker. And then I added an alpha, which is a transparency, so that you could see the overplotting. So even though there are some people who were young initially who are now dead, it's very few people. And then we have like a lot of density of data of the young people who are still alive 20 years later. Pink and blue, smoker, non-smoker. But it's a little bit hard to tell what's going on. So I'm going to make a new variable in my data set, which is going to be called is alive. So right now I just have outcome, which is alive or dead, alive or dead. But R for logistic regression really wants it to be 0 or 1. So any binary variable you can convert to a 0 or 1, and here's how I'm going to do it. I'm going to make this new variable called is alive. And this is going to be if the outcome is equal to alive, I'm going to put 1. Otherwise, I'm going to put a 0. And this is a mutate, so it's going to stick a new column into my original data set and kind of overwrite that. So I hit play. Now I've got 4 variables in my data set, and I could go click on it, and now I've got is alive, 1 if they're alive, 0 if they are dead. Any questions about that? Okay. So then we could do our plotting again, where I'm going to take this jitter off just for a second. If I just plot this again, this is going to be basically the same as my original plot, but now I have 1 and 0, and it's kind of flipped. So before dead was the top one and alive was the bottom one, and now we're calling alive 1, so that one's on the top. So these are all the people who were alive, and here's the people who were dead. Otherwise, looks pretty similar. But the thing that's nice is now I could put jitter around is alive inside my ggplot. And then that will add a little bit of random jitter to those points. So instead of having them right at 1, it'll go up or down a little bit, just so that you can see the density of the points. So these are all people who were alive in the follow-up, and here are all people who were dead. And now it really solves that overplotting issue. We can see that the vast, vast majority of young people were still alive 20 years later. Just a few of them had died, and they kind of swap in that way. Questions or thoughts? I lost my chat again, but people don't chat me very often. Okay, so we're gonna try and model this. We're gonna try and predict if someone is alive or dead. And just like in linear regression, where we were trying to compare, like, is the flat line, which is the mean, is that as good as using a line that has a slope? We could find the mean for every observation. So I'm going to take the mean of that is alive variable. This is kind of base R code, but this finds that mean. And it is 0.719. And what does that number mean? What does 0.719 mean about my data set? It's the average of this variable, which is just 1s and 0s. So if I take the mean, what do I get? What does that number represent?
Seems like on average there's more alive people than dead, at least.
Yes. Yeah. So it says like the average aliveness of the whole data set is 72%, or you could think of it as just like the percentage of people who were alive in the data. So it's the percent of alive people. It's about 72%. And so that would be the easiest way to model this data, is just say for everyone in this data set, we're just going to predict 0.72 as the aliveness or the probability that they're alive or whatever. And because 0.72 rounds up to 1, that means we're just going to predict that every single person is alive. And we're going to get it right 72% of the time, because 72% of the people are alive. So that's like pretty good, right? Like getting it right 72% of the time. And so we want to try and beat that with our model. We'd like to get it right more than that percent of the time. And so I have some questions here. You know, what would it predict for a 20-year-old person who smokes? It would predict 0.72. It would predict they're alive. So predict alive. What would it predict for a 60-year-old person who doesn't smoke? It would predict alive. It would just predict alive for everyone. Scroll all the way down and back up. There's some bug in my RStudio. And does that make sense? Sure, but we'd like to do better. We'd like to improve our model. So one thing that we could try is to do a linear model, which I don't think is the right thing to do, but we'll try it out. So we're going to try and predict is alive based on age, and I could look at the summary of that model. So it's got an intercept and a slope. I could also do a multiple regression model with age and smoker status. And then these are functions, or this, I guess I'm just using it, the same function twice. Augment is a function from the Broom package. And so you can run it around a model object, and it will sort of create, it's like the original data set, but it just takes the relevant stuff from the data and it puts on some model information. So I'm going to run this augment on M1 and on M2 as well. So let's see. So here's an augmented data set. Instead of having all of the variables from the Wickham data set, which there were 4 of, it just keeps the 2 that were related to the model that I fit, the response variable and the 1 predictor that I used. And then it has a fitted value. So that's the predicted value. And you can see already at the top, like this person is predicted to be 1.1 alive. That doesn't really make sense. This person is predicted to be 1.18 alive. I don't think, yeah, the lowest one is 0.11. So it doesn't go negative, but it's going above 1. So that's not good. And I think the same thing happens with my multiple regression model. Doesn't go negative, but it goes above 1. So I'm not going to try and interpret the coefficients of the models. They don't make sense. The predictions are bad. We don't want to use a linear regression approach. But I could like put the line on there. So here's what it would predict. I could also do the 2 lines for the multiple regression, you know, kind of parallel lines approach. And I'm not going to do the predictions either because not super appropriate to do that. Questions? Oh man, R putting in this like spell check, it's really calling into sharp relief all my terrible spelling. Interpretable? I think that's a word. So we're going to fit a logistic model so that we have better interpretable results. So instead of modeling the probability with a linear model, we're going to model the logit with a linear model. And that's going to give us something like this for the probability. It uses maximum likelihood estimation. Here's something that's pretty important for the homework. So to fit a logistic regression model, you use the GLM command. So GLM stands for generalized linear models, and it can fit a bunch of different variations on linear models. So if I don't put anything at the end here, so if I don't put family equal binomial, it's going to fit a linear regression by default. So if I run this and look at this summary, those coefficients 1.48 and negative 0.016, those are going to be the same as from my my linear regression before, 1.48 and negative 0.16. So it's important when you use GLM, if you want to do a logistic regression, you have to say family equal binomial. So that's what makes it do the logistic regression with that logit link. So that's an important thing. If I run this and then I look at the summary, this is going to be different than the summaries that we've been seeing so far. Instead of having the residuals, it has the deviance residuals, which we'll talk more about next week. It still has a pretty similar table for the coefficients. It's got the estimate, it's got the standard error. It has a z value rather than a t value. And I'll admit, I don't remember why it changed from linear regression. I should look into that. It still has a p-value though. It doesn't have an r squared or an adjusted r squared. It doesn't have the f value for the whole model or the p-value for the whole model. But what it does have is AIC. So we talked about AIC in the variable selection section where we're doing like backwards, forwards, stepwise, best subsets. And I was saying, you know, this is a way to look at a model and see how good it is. This is why statisticians like AIC, is because it works on linear regression, logistic regression, machine learning models. Like you can do AIC on all kinds of things and compare them. So, so there's the AIC value. AIC, it's kind of sad it doesn't have like a nice sentence like R squared, but at least you can use this to compare between models. Any questions or thoughts about this table? Okay. So we want to try to interpret some coefficients here. Oh, maybe I was trying to do it here. I don't know. So we could interpret it in the log odds space, and we could also interpret it in the odds space. So I'm going to start in the log odds space, even though that maybe doesn't make as much sense to humans. But I'm going to say a 1 unit increase in age is associated with a 0.12 decrease in the log odds of being alive. So that's the one that is kind of similar to the linear regression sentence. A 1 unit increase in that explanatory variable is associated with and then you sort of put in the slope and say an increase or decrease, and then the log odds of whatever your response variable is. So that one is, you just read off the table. But the odds is the one that is probably more useful for humans. So this one would be a 1 unit increase in age is associated with changing, I'll say multiplying the odds of being alive by a factor of, and then I need to exponentiate this coefficient. So I'm just going to copy it, and I'm going to do exp parentheses and then paste that number in there by a factor of 0.886. And so anything that you multiply by a number less than 1 goes down. So this means that is the odds of being alive go down over time. So let's say, when you're 20 years old, your odds of being alive are like 10 to 1 or something. I don't know. So your odds are 10, and then you get a year older. Now you're 21. We multiply your odds by 0.886. Now your odds of being alive are 8.86 to 1. And then you get another year older, and we multiply by 0.886, and your odds go down again. So it's not going down linearly, but it is going down by a multiplicative constant factor. Thoughts about that? Okay. Yeah. Okay. I have like a million thoughts. We'll see what we end up getting to today. So this is what I was saying. I'm sort of going into chapter 10. You could also do a generalized linear model with family binomial, and you could put more than one predictor into that model specification. So I could have age and being a smoker, and I could look at the summary of that model, and I could interpret these sentences. I'm going to just copy the ones from above because I think the age stuff doesn't change a huge amount. So a 1 unit increase in age is associated with it's still a 0.12 decrease in the odds of being alive, but now I have to put in holding smoker status constant. And then same thing here, a 1 unit increase in age, and then I'll just stick on here, holding smoker status constant. And then we could do the same thing, the log odds and the odds that have to do with the categorical variable. So in the log odds space, compared to non-smokers, smokers have 0.2 lower log odds of being alive. Is that right? Compared to non-smokers, the ones baked into the intercept, smokers have odds that are 0.2 or log odds that are 0.2 lower. Holding age constant. And then we'd need to exponentiate this number to know what it is in the odds space. So then I could say, compared to non-smokers, smokers' odds of being alive are multiplied by a factor of 0.81. That is, their odds of being alive are lower, and this is holding age constant. I guess the last sort of code thing is you can just, copy the coefficient and then do exp parentheses and paste it in. You can also do exp of coef of log m1. Oh, too helpful, RStudio. And then it'll just exponentiate all the coefficients. We don't usually interpret the intercept in logistic regression. It gets sort of even less useful than in linear regression. But this is handy when you have 2 or 3 or a bunch of variables, then you don't have to copy, paste, and exponentiate them all separately. And now I've forgotten the names of those, or the numbers of those 2 questions, but one of them wants you to do a confidence interval for the coefficient, so like basically in the log odds space, and the other one wants you to do a confidence interval for the odds ratio, so in the odds space. So let me just, let's do a simple logistic regression. So this is my simplest logistic regression for the age coefficient. So if I wanted to do a confidence interval in the log odds space, I could do it by hand. I could take my estimate, and then I have my standard error here. So it would be like plus or minus the standard error times. And because we get to use the normal distribution here for reasons I can't remember, you don't have to find a critical t value. You can just use 1.96. So you would do, time that, and then you could do the minus. So you could find the confidence interval by hand, but you could also use the confint function on that log, that model that I did. This should be the same, hopefully. Yeah, in one class this week, I got the numbers wrong, and I still don't know why, but this looks the same. Maybe a little bit rounding error or something, but so confident of your model, you're going to get the confidence interval in the log odds space. And then the other one asks for a confidence interval for the odds ratio. So the odds ratio is that exp of coef of log m1. This is my odds ratio, the 0.88. For a 1-year increase in age, the odds of being alive get multiplied by 0.88. That's the odds ratio. So we want a confidence interval that's centered around 0.88. And I don't know, it's possible you could just exponentiate this. Let's try it. And then this as well. That looks vaguely right. So you could kind of do it from the table and then exponentiate the numbers, but it's also fine to exp of confint of the log m1. And is that the same? Just about. Yeah, again, maybe there's some rounding error because it's not exactly 1.96, so I'm estimating there. And do some two-way tables. I will say, I'm going to show you a couple different ways to code the two-way table, and sometimes one way makes more sense in someone's brain than the other way. I'm going to start with the tidyverse way, and the two-way table that I'm going to do here is about the outcome and the smoking status, because those are both binary categorical variables. So that's like in the Titanic data, alive or dead, and then female, male. So we're going to take our Wickham data, and then we're going to group by, and you want to group by both of the variables. So outcome, comma, smoker. But the order in which you group by makes a difference in the results that you'll eventually get. So we can look at it both ways and see which way we actually want. And then I'm going to summarize. And what I'm going to summarize is n is equal to n, open paren, close paren. Just do that much here. So this shows me how many people are in each of these categories. So I've got 502 people who were alive and not a smoker, 443 people who were alive and a smoker, 230 dead, not a smoker, 139 dead, yes, a smoker. But I might want actually the percentages. So I'm going to just hit the up arrow a couple times and edit my code. I'm going to do Wickham, and then group by, and then summarize. And then I'm going to do one more thing. I'm going to do mutate. Prop is equal to n divided by sum of n. And this gives me some proportions. So this is where the order in that group by really comes in and matters. So this one I can hopefully see by adding up 0.53 and 0.47 that adds up to 1. And then down here, 0.62 and 0.38, that adds up to 1. So this is saying of the people who are alive, what percent were smokers? Of the people who were, or non-smokers, of the people who were alive, what percent were smokers? 0.469. Of the people who were dead, what percentage were non-smokers? 62%. Of the people who were dead, what percent were smokers? 38%. But if I swap, so I'm gonna hit the up arrow a bunch of times, I'm gonna swap the order in my group by. So I'll do smoker, comma, outcome, and then that same summarize, and that same mutate. Now, these two things add up to 1. 0.69 and 0.31, that adds up to 1. So this is, of the people who were non-smokers, what percent are alive? Of the people who are non-smokers, what percent are dead? And so you can make the argument for this homework question, 9.28. You could make it sort of either way, but you have to kind of think about what it is saying to you in terms of the percentages. Are there thoughts about that or questions? Okay, I'm going to show you one other way. So this is more of a base R way. That was the tidyverse way. You could also do a table of Wickham, $, smoker, comma, Wickham, $, outcome, for example, and then it makes a little two-way table for you. This is more of the kind of like tall format of the data. We were talking about this a little bit with ANOVA of like tall data versus wide data. This is a little bit taller, and this one is a little bit wider. And with this one, I don't know if there's a way to get it to give you the percentages. So you have to calculate it yourself. So if you want to know, like, of the people who are alive, what percent of them smoked, you have to do the denominator yourself, 502 plus 443, and then you need to say, okay, well, 443 out of that is 47% of them, or 502 out of that is 53%. So those are the numbers from up here. But you could also do it across a row. So add the denominator of 502 plus 230, and then do something like 502 out of that. This would be that number. And same thing, 230. That's that one. So I don't know which one you can use, however it makes more sense in your brain. This one maybe forces you to think more about the denominator, and this one, the denominator is, the decision is made by how you decide to group your variable. But either way, I think with the Titanic data set, you're going to find more females survived than males. I think that's kind of the Titanic story is, you know, women and children first.